This conference will now be recorded.
Good evening. Today we are going to discuss the motion of center of mass. So still we are in this chapter, system of particles and rotational motion. And in the last class, if you remember, we had discussed the center of mass, the definition part, and we had also seen how to mathematically write the coordinates of center of mass. And if I write for n number of particles, the vector notation of center of mass, how was that? It was this. This mass is the total mass of all n particles, and then it was mi ri. This is also these are the position vectors of individual particle, and I can go up to 1 to n. So if we rewrite this equation, how we get m r, then m1 r1 vector, m2 r2 vector, and like that it goes up to n nth particle. Okay, so this is the definition. We have seen the position coordinate vector, like position vector of the center mass. So this capital R is position vector of center of mass, of center of mass, and small ri's, these are actually position coordinate, position vector of individual particles. So this is the position coordinate of a particular point where the whole mass is concentrated. Okay, so that is center of mass. Okay, so this is the definition. So definition wise we are now okay. Now in the beginning, also in the introduction part, I had discussed that for extended bodies, if when we have used the laws of motion or Newton's laws of motion, we had taken extended bodies as single particle. But in this chapter, system of particles or rigid body, in this chapter we have come up with another concept that is called center of mass, where if you look the center of mass, like a motion of the center of mass, this will give you the whole picture of the motion of the system of particles. So this is what we are going to see today. So today we'll actually see the significance of center of mass. We have come, see, I'll just remove this portion and see, if we take time derivative on both sides and assuming that the mass of each particle, individual particle, do not change, like does not change. So if I just take time derivative, okay, take derivative with respect to time on both sides, assuming mass to be constant. That means when we take time derivative, we'll take only for position vectors, not for the masses. That would give rise to 0. So look, this is dr dt. Similarly, it will be m1 dr1 dt plus m2 dr2 dt plus dot dot up to nth particle. It will be like this. Okay. So you can see this is the velocity of the center of mass. So I can write this as VCM, and see these are velocities of individual particles. Okay, these are nothing new. We are just trying to understand some good or underlying physics in this. Let us write first this one. Okay, so this is MVN. So you can see this is actually, this VCM is the velocity of the center of mass, and these are velocities of individual particles. Now what we'll do, we'll just take derivative of this equation also. Okay, time derivative of this equation. Okay, let us clean some of this because I have. Okay, so let us take time derivative of this equation. Let us say this equation is equation 1. So if we take further time derivative, what we get, m dvcm dt. So this will be m1 dv1 dt plus m2 dvt2. Okay, so this is going like this way. So look here, this is the acceleration. So I'll remove this part also. I'm just taking time derivative. Okay, see, I had taken first time derivative of position coordinates or position vectors, and then I'm taking time derivative of the velocity vectors also. So look, this one can be written as the acceleration center of mass, and this will be a1, suppose the vector notation, a2, like that it goes. So you might be thinking these are very trivial. Why do you write this much and then you are like what new physics you are going to bring over here? Yeah, look, there will be some new physics over here for the system of particles. See, we know m into acceleration from Newton's law. What we know, force is equal to m into acceleration. Okay, so this side, this is acceleration, this is the mass of the whole, like all n particle system. So I can write this as F on center of mass. Look this, and these are actually masses of individual particle. Sorry, the forces on individual particle. F1 plus F2 plus dot dot up to Fn. Okay, these are all vectors. So these forces, these forces we have. If I have a system of particles, n particle system, n particle system, so they have two types of forces. One is see, if I write forces, see, each is for each particle. On each particle, there will be two types of forces. Suppose I write for particle 1, there will be force, that is internal force, okay, and another one will be external force, okay. So what do you mean by internal force? We had, I think we had discussed somewhat before. So internal forces means this mutual interactions, repulsion, attraction, etc. So those forces, and according to Newton's third law, these internal forces, suppose I take two particles, so this is 1 and this is 2. The forces on 1 due to 2 will be exactly equal in magnitude and direction will be different, okay, to this. So if we take summation over all these internal forces, so this is actually according to Newton's third law of motion. Newton's third law. Okay, according to Newton's third law of motion, internal forces are just like action and reaction. So if we take the summation over all these external and internal forces, sorry, this will give you this force on individual particle. Okay, so individual particle has forces due to external agency and forces due to internal force or internal attraction, repulsion, etc. Among themselves. And as we know, these forces are actually action and reaction. So if you take summation over this internal force, this will give rise to 0, and this will give you total external force. Okay, total external force. So in this, I'll just remove this part and let me write the total force on the center of mass is the sum of all the forces acting on each and individual particle. So when we take the sum of internal forces for each and individual particles, that internal forces give rise to 0, and hence the force which acts on the center of mass is summation over external force alone. Okay, the whole, like the whole force which is acting on the center of mass is the external force. Okay, so look, from this equation how we can write, what we can write is, see, m into a acceleration of cm, okay, with the vector notation we can write, and see this this is like this, okay, summation over I, and this is obviously for external force, external, okay. So what does this mean? If there is a motion of the center of mass, if there is a motion of the center of mass, the motion of center of mass is such that it describes the motion of the whole object, whole system of particles. And from this equation what we can say is that the center of mass is moving as if the whole mass of the system of particles is concentrated at the center of mass, and the motion of center of mass or the forces acting on center of mass is the sum of all the forces acting on individual particles. So what we can say that the motion of center of mass as if, so a motion of center of mass is happening such that the whole mass is concentrated on cm, center of mass, and the force, obviously external force acting on cm, center of mass, is the sum of external forces acting on all the particles. External forces acting on all the particles. Okay, so that is the thing. So what we have got, m is equal to a cm is equal to summation over mi ai, and obviously this is for external force. External force, that means to a rigid body, external force means some agency has to give some force on this system of particles. So this is external force. External force. Okay. So from here what we can conclude is, see, in the fifth and sixth chapter we had considered object board, like extended object as point object, and doing that approximation we have used laws of motion. Okay, so we have used laws of motion. Laws of motion has been used, okay, has been used for or applied for extended object. So extended objects, assuming the them the extended objects, them to be point object. Okay, point object. So extended object has been approximated to point object, and then, or point mass. So and then we have used Newton's laws of motion. But after introducing center of mass, what is the main advantage is, if you just analyze the motion of the center of mass, then motion of the center of mass, then the motion of the whole body is described. Okay. One more thing here you need to understand, that here we have not specified the rigid body, whether there are like forces, like how many forces are there internally, and what is the motion of each and individual particle, whether they are rotating or translating alone, or they have combined motion, etc. Those are not of our interest. We can actually, we can actually have the information of external forces, that alone is sufficient to describe the motion of a rigid body, instead of thinking of all sorts of motions or considering all sorts of motion in for individual particles. We can describe the motion of center of mass, which is again a point where the whole mass of the object is concentrating, and once we know the motion of the center of mass, then we know the motion of the whole system of particles. So this is the significance of introducing center of mass. Now look, see, center of mass of a system does not change. So center of mass, like motion of center of mass does not change if the external force, external forces or force acting on the system remains constant. Acting on the system remains constant. remains constant. I'll explain what it is. See, let me just take up this example. Suppose there is a cell, okay? Cell, you have just thrown it just like a projectile we have learned in previous classes, previous chapters. So you have just thrown it like a projectile, and as you know, projectile will undergo a parabolic trajectory. Okay. So what happens? This cell on its path, path like on its due course of motion, it explodes into multiple particles. So suppose, see, as you can see from here, there is a cell which has been thrown just like a projectile, and we know projectile is actually the motion under gravity purely, and for that case the trajectory of the motion of the projectile will be a parabolic path, symmetric parabolic path about its maximum height. Anyway, and see, for that case, you know, like center of mass, see, center of mass also follows the same parabolic path. So when you throw an extended object, its center of mass actually undergoes this, like undergoes motion in this parabolic path, the center of mass. Now suppose on the due course of its motion, it gets exploded, okay, exploded and turn into various pieces, okay, various pieces, and the pieces, ideally we have taken two pieces, and their motion, look, since, see, their motion, you know, like this, suppose this is one particle, like one fragment of the cell, another fragment is this one after blast. So they can actually like move in different trajectory because of their change in the velocity or energy. They can actually go through different trajectory, but the center of mass remains on the same parabolic path. It will, center of mass will continue to go up to the ground. Okay, so center of mass will undergo the motion in the same trajectory, same parabolic trajectory, even if the cell is now broken into pieces. So how does it happen? You know, we can show from here. Suppose we have, see, suppose we have this one. So this is actually m into a cm is always exactly equal to the external force, sum of the external force on the individual particles. So the motion does not have any impact or any effect of internal forces. The motion of center of mass does not have any effect on, like any effect due to internal forces. And you know, when any object, here the cell blast into pieces or explodes into pieces, that is actually due to the internal force. So here, you know, the blast is actually happening due to internal forces, internal forces. So forces, but you know what happens here, the external external force, that is what, that is the gravity, because projectile motion is under purely gravity, that is gravity remains constant. So as we had spoken, like as we had learned in the beginning, that if you have your external force constant, the motion of the center mass does not change. So that's why even if this cell is actually blast explodes into multiple particle here from here multiple particle, they may follow different trajectory, but the center of mass will follow the previous trajectory itself. Okay, so this actually explains you how the force on center of mass or the motion of center of mass is only affected by external forces acting on the rigid body, not due to the it will be so the motion of the center of mass will not be affected by internal forces whatever changes happen. Okay, so yeah, so this we have already discussed. Now we'll go to the momentum part. So momentum, conservation, and motion of center of mass. So since center of mass is moving, so there will be linear momentum as well as angular momentum. So we'll see that what all those things are. So as you know, linear momentum is given by P, and if I write this is for center of mass, this will be m into v cm. Okay, so what is this m? This m is actually the mass of the whole object if it is a system of n particles. A system of, suppose you take a system of n particles, n particles, system of n particles. Okay, so you can write this on the right hand side as I was showing you some time back. It will be the momentum, total momentum of the center of mass will be actually the summation over the momentum of individual particle. Okay, this is m2, and this goes up to nth particle. Okay, all right. So see, this is the momentum, and also we know uh, from Newton's second law of motion, Newton's second law, from Newton's second law of motion, what we know? Newton's second law of motion. What we know is dp dt, so dp cm dt will be is equal to, so these are individual momentum, I can write p1 p2 etc. So dp1 dt plus dp2 dt etc. I can write for individual particles also. Okay, so these are the things I can write. Now look, this dp dt means what? This dp dt means actually external force. This is according to Newton's second law of motion. Dp dt is equal to external force. If the external force is zero, then what you get is, see, this implies that dp cm dt is equal to 0, which implies that pcm is constant. So when there will be no external force acting on center of mass, then what will happen is pcm Yeah, madam, is it audible now? Is it audible? Then I can continue. There was a power cut, so my Wi-Fi got off. Now I'm actually taking the class from mobile network. If it is very clear, if you are able to hear me properly, then I'll continue.
Yes, Ram, I can hear.
Okay, good. So, so we have seen what is conservation of momentum of center of mass. So, if external force, so how we can write this? If external force is absent, the momentum of the center of mass will be conserved. Okay, so that is what we can conclude from here. Okay, now what we'll do? We'll we'll see. We have learned equations of motion. We have learned equations of motion in case of linear, uh, in case of single individual particle, and also we have. So this is actually, we'll just see when there is a rigid body and it undergoes a rotational motion. Okay, when there is a rigid body like this, and it has suppose n particles, n number of particles, and when it undergoes a rotational motion, okay, undergoes a rotational motion, then what are the equations of motion in rotational motion? Okay, so I see you might be missing some points. Let me tell you. In case of linear motion or translation motion, what we have got? Equations of motion. So equations of motion for translation. Translation. Let me just write down so that you can recap by yourself. So you look, the final velocity, if I think v, and initial velocity u, and uniform a, acceleration a, and suppose a body translates with initial velocity c u and uniform acceleration after time t, after any instant of time t, what will be the velocity? So we know, so this is first equations of motion in translational motion. So v is equal to u plus a into t, or this can be minus also depending on the acceleration or deceleration. So this was first equation. Second equation, you can find out after certain time t what will be the displacement s is equal to ut if you have the initial velocity given to the object. So this also depends on the sign of the acceleration, whether it is negative or positive. So this is called displacement. And the third equation, you can find out from here, v square is equal to e square plus or minus 2as. So these are the equations of motion we have learned actually in kinematics for translational motion. Suppose when an object is rotating, when an object is rotating, see, in a uniform circular motion, we have learned that angular velocity, angular velocity, angular velocity is written as omega. Angular displacement, angular displacement, angular displacement is given by theta, and angular acceleration, angular acceleration acceleration is given by alpha. Okay, and they have, see, specific relations, like, see, you have v is equal to r into omega. Okay, so suppose this, there is an object which is moving along a circular path of radius r. So if you have translation like speed, linear speed v, okay, then v is equal to r omega. This we know. Even linear acceleration a is equal to r alpha, or alpha is equal to, sorry, yes. So a is equal to r alpha. This is what we know. Okay. So these are the things we can use in case of rotational motion also. Okay. So let me derive the equations of motion for you. Equations of motion. Equations of motion for rotation. Okay. These are. So let me first derive the first equation, that is, the in case of rotational motion also it will be final velocity is equal to u0 plus alpha into t. So this will be the first equation if we take the rotational analog of these equations of motion. Okay, so this is the first equation we have to prove. We will take or adopt the calculus method. So suppose, what we have to suppose, we have to suppose that the object starts with omega 0 angular velocity. Okay, angular velocity, and it has alpha, that is uniform uniform angular acceleration, ACC. Okay, so this is the short form of acceleration. Okay, so if I write in terms of, okay, let me write at t is equal to 0. So this thing is the velocity is this. Okay, so at t is equal to t, at any instant of time, t is equal to any instant of time, velocity may be this v. Sorry, velocity, angular velocity omega may be this omega. So what is the expression? So how do you get this expression? So in this case, we know alpha is equal to d omega dt. Okay, d omega dt, similar to this, a is equal to dv dt. Okay, so this are analogous anyway. So from here you look how you can do. You can just integrate it. So so this is alpha into dt. You integrate this side, t is equal to 0 to t, and this side you can integrate from omega 0 to omega. Okay, so you can see from this, if you integrate, you'll definitely get omega minus omega 0 is equal to alpha t, and from here you can find out alpha 0 plus alpha t. So look, this is the equation of motion which we were intending to derive. So we have got it. So this is how you can derive this equation of motion, and this is actually, just analogous to your equation of motion what you got for translation motion also. So similar to that, see, we can find out the second equation of motion. What is that? That is theta is equal to u0, that is w0 into t plus a half alpha and t square. So this we have to prove. So to prove this, what you have to take, the similar things you have to take, like at t is equal to suppose 0, we know omega is equal to omega 0 with initial velocity, and at t is equal to t, omega is equal to omega, all right, and uniform acceleration, angular acceleration is alpha. So we will go from the definition of velocity omega. This is the d theta dt. Just analogous equation, we know velocity is ds by dt. Okay, so this is the analogous quantity in translational motion. Now look, if you just integrate it, what you get? Omega dt, this is theta. Okay, if you integrate it, and we have got omega is equal to omega 0 plus alpha t. If we put this here and take omega 0 to omega limit, and here you put it omega 0 plus alpha t in place of this, and then integrate it. Okay, this will be 0 to theta. Okay, or sorry, the theta 0 to theta also you can go with. So if you integrate here, what you get? You get omega square. Okay, so omega, sorry, this is omega 0 t plus half alpha t square is equal to theta minus theta 0. Okay, or you can write this as, so this is the initial displacement. If I take this as 0, initially maybe theta 0 is 0, so you can get this as omega 0 t. This is the initial angular velocity plus half alpha and t square. So this will give you the displacement at any time if you know omega 0 time and alpha. Okay, this is the equation for angular displacement. Now we have got the third equation, so which we will derive now. So this you have to get omega 0 square plus or minus whatever we are taking as positive acceleration over here. So 2 alpha and theta. So this we have to find out. So to do that similar thing, here we can do alpha is equal to d omega dt, we know. So this can be written even d omega d theta into d theta by dt. So look this, as if this goes off and then you get d omega dt alone, and this part d theta dt, according to our definition of angular velocity, we get omega. So d omega into d omega d theta. Okay, so now if you integrate this, see omega d omega, taking limit omega is equal to omega 0 to omega, here take alpha into d theta, and again if you take this theta as theta 0 to theta, so you will get uh, this, you just integrate it, you get, and put the limit, you get omega square minus omega 0 square is equal to, so here will be half factor here, so you can multiply here alpha into theta minus theta 0. So if you take theta 0 to be 0, then you get this exactly this equation. Okay, so this is how you can derive. Now you might be thinking, sir, you are deriving very nice, but where we would apply these equations of motion? I'll take up one simple example, then you can understand where we can apply particular particular equations of motion in case of rotational motion. So these are the kinematic equations in case of rotational motion. Okay, look, I'll just take you through one simple example. Suppose I'll just write it: the angular speed of a motor wheel, the angular speed of a motor wheel is increased from 1200 rpm to 3120 rpm. Okay, rpm in 16 seconds. Okay, 16 seconds. Then what is the, so question is, what is the angular acceleration? Angular acceleration. Okay, this is question 1. And how many revolutions does the wheel, how many revolutions how many revolutions does the wheel make during this time interval, during the interval of time, or interval, during interval. Okay, so this is what is the question. So look here, the initial angular speed, so I can write from this given what are the given parameters. So look, this rpm actually, this is revolutions per minute. So this is actually initial rpm. So this rpm, I'll write for you what is rpm. rpm, sometimes it is written as small rpm also. So rpm means actually revolutions per minute. So from here you can find out the omega 0, but how to do that? So you have to make it rps. rps, what does this mean? Revolutions per second. Okay, you have to make it revolutions per second. So revolutions per minute is given, so you can write rpm divided by 60 second. 60 second means 1 minute. Okay, so you are just dividing with the minute factor, so you'll get this is rps. And rps means what? rps means frequency. Frequency. Okay, rps means linear frequency, that is new. Okay, rps. So whenever there is a problem given with rpm, so if you have, suppose here rpm is given, rpm, so what you have to do, you have to find out new 0 here. Initially it was new 0. rpm you have to divide with 60 so that you get rps. And once you get this c6, so this will be 20 rps. And once you get this rps, you can get 2 pi into rps or new 0. So 2 pi, so this will be actually uh, 40 40 pi. Okay, into, so 40 pi, 2 pi into new 0 is 20. So you get this omega 0 here. Similarly for the final, so it is increased to how much? So from here actually you will get to new. So what was the new? Suppose 2 pi into rpm, rpm by 60. So this will give you omega. So what was the rpm? rpm was 3120 divided by 6. So you get actually here 50. Sorry, let me check. Yeah, so 5 and 2, I think this one. Okay, so you get into 2 pi, 2 pi. Okay, so you get exactly 104 pi. Okay, 104 pi. These are actually in radian. Okay, so when you write rpm by 16 to 2 pi, this will be converted to radians. Okay, radians. So this much radian. Since pi is there, so it will be in radian unit. So once you get these velocities, and see this velocity was changed from new 0, this is omega 0 to omega in how much second? In 16 seconds. Okay, now you can find out what is the acceleration. What is acceleration? We know. So we know final velocity is equal to initial velocity plus alpha into t. So from here you can find out what is alpha. So that is final velocity minus initial velocity divided by, this is angular velocity obviously, divided by t. See, both you got now, both you got, and you know the time is 16 seconds. So look here. So 104 pi minus 45 divided by 16 seconds. So this will give rise to, so this will give you actually rad per second. Rad per second So I'm sorry, this will be radian per second, omega radian per second. This will be radian per second square. Second square. Okay, so radians per second square, and you look, this will be actually equal to 4 pi, some 4 pi radian per second square. So this is the angular acceleration for this problem. Similarly, if you want to find, so you have got now, see, informations about new, see, omega 0, that is 40 pi radians per second, rad per second, and you know the final also, this is 104 pi rad per second, and you know the time it took is 16 seconds from changing to this. You know the alpha also. What is the alpha? It is actually 4 pi. We have seen this is 4 pi rad per second square. Okay, now you have to find out what is the displacement, or like what is, like how many revolutions does the wheel make, how many revolutions does the wheel make. For that, actually you have to find out what is angular displacement. After doing that, I'll tell you what it is. So this is half alpha t square. So t, you know this. So 40 pi into t16 plus half alpha is given 4 pi into 16 whole square. So if you calculate it, this theta, you will get as 1152 radian. Okay, this much is, so for a complete revolution you have 2 pi, right? Complete revolution, this theta goes from 0 to 2 pi, whole 2 pi. So for complete, for one revolution, it is, displacement is 2 pi. Okay, theta is 2 pi. So for this much radian, how many revolutions will be there? So you just divide with 2 pi, that's all. So if you divide with 2 pi, so you will get the number of revolution. Okay, number of revolutions. So this will be somewhere near to this many number of revolutions. Okay, so how many? 576 revolutions. So this is how you have to use. See, in case of angular motion also, or rotational motion also, you can use this equations of motion and solve numerical problem. Okay, so these are the kinematic equations for rotational motion. So we'll stop it here today. You can take up various example problem, or we have actually given already. I have given MCQ and quiz on this chapter. You can look forward these questions, like related to this chapter, like see this using how you can solve these problems, like kinematics problem in rotational motion. Okay, so we'll stop it here for today, and in the next class we'll be learning the turning effect, torque, etc. We'll be learning, and we'll be solving few numerical problems in that. Okay, so turning effect is very important. In various exams you will get this kind of problem, like turning problems related to turning effect. Okay, so bye for today. We'll meet again on Thursday. Okay, bye.